Hi all, this is Claudio from expertfea.com, bringing you a new live stream. Today we are talking about the fracture of concrete columns during 3-point bending, and we're going to use two different methods of approach. I'm talking about the traditional Lagrangian mesh and the smooth particle hydrodynamics meshless option. So with small spheres. You'll see in a few minutes what I'm talking about. Now I'm sharing my screen. A quick reminder about my website. Feel free to solicit our tutorials, simulations, books, live streams, and whatever suits your need. I took the liberty of opening ANSYS workbench, and we're going to do these simulations in explicit dynamics. Because the problem is pretty straightforward and simple, I will do my own geometry ad hoc live. So let's open Space Claim. And here, let me open YouTube. And we're going to watch ANSYS concrete when the time will come, all right, while the FEA is solving. So let's see if Space Claim opened. Yes, it is open. I was talking about a 3-point bending. Let's take an inspiration. Concrete fracture. So we are going towards something like this. Yes, we have 3-point bending. So let's see if it will crack something like this. Maybe we have something like this also, but I'm interested in more on this simulation, on this type of fracture, because it's close to what I have simulated in the past. So let's make a quick model. Let's make it, I don't know, maybe 50. This means 500 in height, yes? How much should it be? I don't know, 2 meters. Yeah, why not? 2 meters, and the height should be let's zoom in if possible. The height should be, I said 500, I said. So let's assign here 500. I think it's kind of too much. 300 maybe. All right. Why not 250? Why not? So again, 300. Let's go with the supports. Should we make them here or not? What do you say? Let's make them here, all right? So we have a middle. This is the middle, all right? In order to have a perfect, let's say, symmetry, all right? So I'm not interested in exactly snapping it, because otherwise it will make a single part. 176 maybe. And maybe let's move it more towards here, something like this. All right, let's mirror what we have. Design, mirror. It asks for a mirror plane. We're going to select an axis. And we're mirroring this. You can see it on the right. Also upwards. Let's make something to press. Yes, to press upon. With Control pressed, we're doing something like this. Let's see if I can. Can I assign paint maybe? Coincident. Does it work? Oh, yes, it worked. So let me move this. I didn't constrain this axis. Can I somehow lock it? We have vertical constraint. Do we have fixed constraint? Horizontal? Fixed constraint, yes. On this axis, all right. So also on this axis, maybe something like this. Because I like to pull this circle, all right, and it doesn't move the axis. This is enough from my side, opinion, according to me. Let's go with what we have. So, even though it is only one surface, there will be different parts, all right? Let's go how much? Because we're going to make a basic scenario. Let's say for beginners, we are going to have a small thickness. We don't need to waste so much mesh, all right? Because the behavior in a section, let's say transversely, will be the same, no matter the thickness of the entire assembly, yes? So I will not go, 100 is nice with me, all right? Because I would like to save some mesh, let's, you will see in a few seconds. Let me move this a little to be more in touch with what we have here, maybe 2.45. Yeah, 2.5. Or maybe 3. Oh, maybe 4. No, 3.5. All right. In here, let's move this again. Almost touching, but not exactly. All right. 4, 4.5, 4.3. All right. So it's touching, but not exactly. I would like to cut these cylinders in order to save mesh. Yes, so let's do like a plane. I selected the face, design, plane here. And I will kind of move it. Yeah, until it, let's say we have a center here. 50, it's all. No, it's almost a center, right? Then I will also do the same here. Let's go something like this. And let's write 400 is nice. All right. So now let's split these bodies. I will split this body with this plane. And I will delete this half. I will split this, exit the command with skip. I will split this body and this body with Control pressed. I will split them with this face, with this plane, and remove this and this. Ladies and gentlemen, we have the geometry. I think we can exaggerate a little more. I mean, these faces, I would like to move them more. Because I didn't move this with the same amount, let me mirror this one. All right, so I will click this plane, move, and double click this axis. When I'm double clicking, it will rotate with 90 degrees. It will be exactly in the middle. We're going for mirror. Select body to be mirror, this one. So now we have the perfect alignment as the left one has. So I promised to further on cut here. Let's cut a little more. 10 millimeters. All right. Do we cut here also? Why not? 10 millimeters. Move. Yes. Let's save the project. The project will be named Stream 10. Stream 9 was with the CFD simulation. Stream 10, January 21, concrete fracture. Configure fracture. I will say classical and SPH, smooth particle hydrodynamics. So I saved it. Let's also save again. Maybe here, close. Let's look a little on YouTube and see if someone has wrote something. Yeah, nobody has written anything. This is perfect. Let's go now to define the concrete material. Yes, double-click engineering data. We can, let's leave this the structure still for supports, for the ones on the lateral sides, and also for the pushing part. And here, from the explicit materials library, we will add it's loading the materials. We will add here concrete. There are, of course, various types of concrete. Let's choose a weaker one. I think this phase at 35 megapascals. Add to engineering data. Look here, all right? So it's defined with RHT concrete strength. Oh my God, so many parameters. What is RHT concrete strength? RHT concrete model. Let's see. It's expressed in terms of 3 stress limit surfaces: the initial yield, elastic yield surface, the failure surface, and the residual friction. Oh, perfect. Ah, 1, 2, 3, maybe, yes, RHT. This is the card for the LS Dyno material. All right, it's perfect that we already have it defined in, this is due to a blast here, but we are going to perform a 3-point bending until fracture is reached. And then we have polynomial equation of state, and here P alpha equation of state. Oh my God, who is an expert? Surely knows these material laws. Surely they should know it the best. Then now we're expecting for ANSYS workbench to open, which just happened. It's not reinforced concrete. We'll leave the reinforcement for another stream. Now we're focusing on the difference between traditional mesh and meshless elements. Let's say the SPH, the smooth particle hydrodynamics approach. I'd like you to see it. All right, so this is what we have, sincerely, because let's name them. This is concrete and these are the support. This is the pusher and these two are called support. We rename with F2, all right? These can be rigid. The concrete at this moment is a Lagrangian defined body. Yes, the reference is Lagrangian. We will instead choose the material to be concrete, 35 megapascals. Connections. Do I need connections? I don't think I need. Let's delete them because you have the default body interaction, which is frictionless. Just for fun, do we have a steel concrete friction coefficient? Just for fun. I hope this is not the rebar, the reinforcing. Dry raffle cast in place. 0.5. General range static 0.2, 0.8. To steel to concrete to be in the order, I will apply 0.65 for wet. Concrete to steel 0.45. I feel look here, drops to 0.4 when sliding is initiated. Let's go with 0.4, 0.45, all right? So here, instead of frictionless, we're going towards 0.4. For the mesh, I prefer to choose here capture curvature no, and here for the quality smoothing low. Let's generate mesh. All right. How small should we make it? Let's begin. Sizing. Control B to select bodies. This is the concrete. Should we make this, I don't know, maybe 7 millimeters? And these 3 sizing, let's make them maybe 10. Right click, rename based on definition, right click, rename based on definition, generate mesh. The more elements we'll have, the longer the solving, all right? It looks so nice. Almost 200,000 nodes. Instead of 7, maybe let's go for 9. And here towards 12. I would like to have results in this live stream, not in the next year. So I like this, and it's below 100,000. No, let's, you know what, let's give it a try. So, SPH dynamics. Let's fix these 2 bodies and apply a displacement. How much should it be? Let's say a fraction of the height, all right? Maybe 70 millimeters, 100. Well, let's do it 100 millimeters. This means 10 centimeters. Displacement of this part on the x axis. We don't care about displacement on other axes. Let's make them 0. That's all with the boundary condition. Boundary conditions. And how much should be the end time? This will be a small pickle. Of course, this is not extremely realistic, but let's try and see how much the solving takes, all right? So, for example, here and here, I would like not to have retain inertia of eroded material to avoid the small red points that fly away when fracture will appear. And here at output controls, let's make result number of points 100. All right, we don't care about this. We will care about this. Let's hit solve and have a feeling about the solving time. All right, let's see if the initial solving will be made maybe in 200 hours. Getting model correct. Error reading in the chi-rep simulation. What is not correct? Loading erased inconcrete failure. No remote points found. This could be a problem. So we have fixed here. We have displacement here. Let's hit solve again. Clear generated data, yes, and solve. No, this problem persists. Should we help with something? Let's help this beam. Let's restrain it a little. I was talking about maybe using a frictionless support, but we don't have. So let's restrain it like this. Control F to choose faces, only these two faces. And let's say that the displacement on the y-axis should be 0. Let's hope it stabilizes the model somehow. Clear generated data, yes. Save. It should work. I don't know why it didn't work. Am I missing something? Let's see. So these are fixed. We have it. This one. We started from 100, all right? It should be a ramping of the displacement. We cannot start with 100, all right? It should be ramping 0, 100, not 100, 100. So here, you know what? Let's suppress this. Clear generated data, yes. Save, solve. How many? I was estimating a few 100 hours. But look here. Yes, we agree. So it's not reinforced. We don't have reinforced concrete. Let's see if... it's reinforced. We don't care about reinforced at this moment. Reinforced. We'll do reinforcing in the next live stream. Concrete microplane model. Reinforced, no? Here, all right. So this is not reinforced. This is reinforced, he says. Mass concrete compared with field data, but it's thermal. We don't need thermal at this moment. Let's look on the simulation. Oh, the same. All right. So here I usually ask for live solutions. Switch to automatic mode, and we can see, for example. Oh, yes. And I will tell you what the problem is in a few seconds. Let's see if we can wait. Should we wait? No, we shouldn't wait because it does not behave correctly. All right. So let's just stop it and let me tell you what needs to be done more in order to have the proper fracture, because the materials are correct. Yeah, let's make a section view. Something like this. Click Edit Section Plane. We're clicking on the hidden line, and this is how it looks like. Let's make it 20 in order to better see the ramifications, okay? There is a tendency, we can see that it's kind of concrete, but something is missing, yes? It's missing a stiffness. Let's say this vertical stiffness. We solve this by, not by asking for more solution results, of course, but by asking for force reaction in the fixed support. Yeah. So I'll tell you how we fix the, how we correct, how we make the deformation of the concrete behave correctly. Yes. So let's animate a little. It's not very nice, all right? So now let's go to here. By the way, we can go for a more realistic time. And let's go, for example, with 1e minus 2. Here the displacement will be changed. Let's make it maybe, I don't know, 200 to have an overkill. Let's make it 75. So if I promised you a better behavior, this is where we should look like. This will allow large displacement, large deformation, yes, but it's suitable for ductile, for materials, and we need maximum strain limit to be something like, from my experience, around 0.42. You will see in a few minutes what I'm talking about. So this will ensure a better, a nicer, a proper fracture of the concrete. All right. And of course, each simulation engineer can correlate this value with the tests, with the visual conclusions, and we can edit that value for the geometrical strain limit. Let's solve like this. Instead of, now we will go towards 15 minutes, 20 minutes solve. I hit save, let's hit solve again, and we will see the new behavior of the concrete. So how much it will take to solve? From my experience, this does not move from this. Let's stop it and resolve it. Does it close? No. Control-Del, Task Manager, Processes. Let's locate the solver. AutoDyn is the solver. And Task, AutoDyn Worker and Task, and it should close the solving. Yes. Right click, clear generated data, yes, save, solve. Do we have any message in the chat? Let's see. Yes, there is a message. Hi, this seems interesting. I never ran simulations like this before. How this industry keeping up with today's economy? Yeah, I don't know what to answer. It is interesting, yes. So take a look and see how it's done. And this is just the beginning, because I have also the SPH method, which is also interesting. Yeah, welcome to the stream. 5 minutes, we can deal with 5 minutes. So I began watching something like this. It's a nice start. I think he also had, or he has some reinforcement, maybe. What? Yes, he has some reinforcement. But judging on how it breaks the contacts, the bonded contacts between the rebar and the concrete, I think it's fully modeled. Yeah, judging also from the mesh of the rebar, it's not a software reinforcement, all right? Because the reinforcement usually is made with the line bodies in ANSYS. Let me show you. So, for example, this is a classic reinforcement made with line bodies. Also here, you see the very slender or thin line bodies. They're not a proper reinforcement. It's not modeled with the bonded contacts between rebar and concrete. Look here, for example, yes? These are line bodies. These are not modeled rebars, not modeled cylinders, all right? So this is, I think, what we have here. We have the option of regarding from how it breaks here the contacts, and also the mesh. This is not the mesh of a line body, but it's a nice trial. Yes, this is what 3 point, but it's carbon fiber sandwich. Yes, we can learn from everyone. Let's see what we can learn more. Analysis of bolt anchorage installed in slab in ANSYS workbench Prashant Patil. I'm interested if does he have reinforcement or not. Oh, we have something here. It's getting far away from what we want to do today. Heavily reinforced concrete structure. This I would like to see. Because if it's what he or she says, then it should be. Look, line bodies, yes? He copied images from different people, he or she. And what software is this? Architectural desktop, maybe? Rebar, so he or she, they don't have the... they have concrete. Linear concrete? What? How can you have linear concrete? Because concrete is not linear. But who am I to talk? Ooh, I think it's imported, as I told you, from an architectural software. Let's see. There is something here. Let's take a look. Let's take a peek of the simulation that we have currently. Oh, so we like this. Yes, we like this because it gets closer to. Yes. Here is reinforced, but here is not reinforced. And there is this triangular region, which we can also kind of see here, breaking. Maybe I exaggerated with the displacement, with the compression, but we will see in a few minutes. So we don't have subtitles. What is this? I'm interested in the reinforcements, and I don't see them. Here, all right. So we have, if he didn't, for the model type, I know that there should be, this is an old ANSYS version, because now we also have reinforcement here in this list. Now the list is bigger with many more options, but it's good also with link and truss. This is at this version, this old version, the reinforcement didn't exist in static. It existed at this time, at this moment in time, it existed in explicit. But nowadays they also inserted reinforcement also in static, besides explicit. This is why it's better to have newer versions. Not necessarily the newest, but newer versions. So let's see a little here. What? Large deflection off? What? Please don't tell me you leave this off. Oh, he left it off. So we'll not have fracture here. Remote force, yes, he's pressing this. Static, all right. So he didn't know how to do it in explicit. Do we have convergence? Yes, there is something. But look here, the scale is grossly exaggerated, and he is going for there is something like a capping of the stress limits. And when you show this option of capping, let's see if I have it here in explicit. Capped isosurfaces. We can somehow in static, we can somehow remove the material if it exceeds certain limit of stress or strain or something else. This is a nice workaround for static and transient where fracture or breakage or mesh erosion does not appear. You can use this kept surface, ISO surface. I will show you in a few seconds. So the FEA successfully finished. Let's go here and animate. Maybe 25 frames per second. And yes, it does something like this. So, all right, to have some plastic strain. So for more realistic values, we need to increase the end time, all right? But for the purposes of our simulation today, I'm not going to increase it because I would like to have results during this live stream. But this, of course, needs to go easily, yeah, on the domain of a few seconds, depending on the test. It is a standardized test, 3-point bending. So yes, this value needs to be increased. For fun, let's make this 0035 maybe. Yes, in order to see some values. Let's also remove the edges of the elements for better visualization. What I would like to see, there is like a webbing of stress and strain dispersion, let's say, and this is what I would like to see. Here, this is what I would like to see. Yeah, this one, this webbing, I like this very much. For example, if I will click this portion, let's only animate this portion. Yeah, this webbing, I like this very much. Retrieve this result. And now let me show you the kept ISO surfaces. I should go for something, look here. So for example, if I would like to somehow, let's not say cheat, but if I would like in static and transient to show some kind of mesh erosion, because for example, I know that at 20 megapascals, the material breaks, let's suppose. Then we can go here on geometry and choose kept surfaces, and it will hide the elements which meet this condition. Yes, which will be above this condition. Look here, kept ISO surface. You see, this is a nice kind of a trick, let's say. This is useful for static and transient. In explicit, we will have erosion, no problem. Let me animate, just for you to see that what we have above this limit, it will be carved out more. And also the material will reappear here. So it's not very realistic. So it broke, then it gets back. Because it's related only to the value. It's not about the realism of the mesh erosion. Yes? This is a way, an workaround in static and transient, not here in explicit, all right? Here in explicit, we do have, let's go back to exterior, we do have mesh erosion. So let's hit here 0, retrieve this result, and this is the resulting picture, let's say. Okay. You know what? Let's be satisfied with this at this moment. Maybe I would like to rerun it with this displacement. Let's see what will happen with this displacement activated. I told you about the kind of a frictionless support for the beam on the y-axis. Let's restrain the beam on the y-axis. And let's see how it influences the simulation. We can write here no beam restraint, and we will duplicate. Do we have any question from the audience? Let's see. No, no new questions. Okay. So this will be with beam restraint. Workbench is opening now. Let's unsuppress this. Yeah, this is zero displacement on the y-axis, on the normal direction. Let's see now how the FEA behaves. I'm curious. Solve. Yes, we're good. Where are we? Here. So this is what he does here. You'll see in a few seconds, I think. I was talking about capped isosurfaces. Because he's in static, he's choosing capped isosurfaces. Look here, yeah? Artificially, it was removed. They are not removed. In reality, they are hidden for a while it meets the second value. This is the threshold. What is above this threshold to the max? Yeah, the upward values will lead to hiding the elements at this moment. It will not be for the entire animation, only at that moment when the threshold is exceeded. In the next frames, if the threshold will not be exceeded, then we will have a reappearance of the hidden elements. So it's a workaround, but not the best workaround to make elements disappear in static and transient. It is a workaround, but not the best workaround. All right, he's making some pictures, force reaction. Let's see the value. What value do we have? 1e8. Considering that this geometry is around 15 meters, then yeah, it could be realistic, let's say. He has some commands. He has some APDL commands. Why? Okay, he knows the best. Look here, what I was talking about. Yes, about the capped. What is above -5, it's kind of hidden. To imitate a mesh erosion, a fracture. Ah, here we can see the reinforcement finally. Yeah. Yes, nice. Nice simulation, yeah, nevertheless, nice simulation. Concrete cube strength using ANSYS software. Let's see. How much does it take here? 4 minutes. Are we on the right track? Let's check. Yes, we're on the right track. This is the nicest view, yes. Let's see what this doctor shows. Maria Rajesh. The name Rajesh, I know he's Hindi. Do we have, yes, we have subtitles. Static again, oh my god. Why nobody likes fracture? Why don't you like fracture? So is he doing another 3-point bending or what? Cube, yes. Given the name, simulation for concrete cube strength. But what I'm interested in is what materials is he using here? We can see the material, concrete. This concrete is taken from where? From the general materials? What? Yeah, from the general materials. So we have no plasticity here. Yeah, these are linearly defined materials. Just a small reminder, all right? And he maybe will fix face and there will be a force on the face, all right. Let's see the amount of force, I'm curious. Do you want to insert another force? You already have a force, come on. Come on. Components, yes, minus y. Minus y. Minus, please, please. Minus, yes. Does he hit apply? Or it's too small. He's parameterizing the wrong component. Yeah. This is a very small load because it's equivalent to 125 kilograms. And yeah, it's too little. Apply, finally, yes. And yeah, this is the deformation. It's extremely small. Maybe you can take a look at the scale and you'll see that the scale is exaggerated because this is not the normal scale. Maybe, can we see the scale? Let's see. No, I bet we will not see the scale. This is exaggerated. Yeah. Look here, being linearly defined. But it's pascals. Okay. It's not megapascals, it's pascals. So it's pretty small, yeah. Negligible. Saving a file. All right. So no scale. Mr. Maria Rajesh, please also show scales, yes? And increase the load. Doctor. I always wanted to see something in robot. Let's see if we have. Do we have? We have design, but no FEA. Here we have something. Yeah, robot structural analysis. It's kind of software dedicated to civil engineering, simulation software for civil engineering. Of course, I think it interfaces with main architectural software, Revit, ArchiCAD, or something like this. Do we have, come on, do we have values? I'm looking for stress strain values. No, no value? All right, maybe another time. What have we here? Oh, it's finished. Let's see the results. And we will evaluate what we like better with the restriction on the faces, lateral faces of the beam, or without this restriction. All right, so save. Total deformation. It is something. It looks kind of the same. You know what? Let's remove it, and here let's make a little, maybe 0.5 here on the geometric strain limit. Why? Because I think it broke kind of too much. All right. Also here, let's make it 140. Save, solve. Then we're going for SPH, for smooth particle hydrodynamics. This is what we want to make, yes? This is 4-point bending, and this is a simulation with SPH, with small spheres, yes? This is what we will make in a few minutes. Does this solve? Yes. 5 minutes, all right. What is this? Fiber cement reinforced in ANSYS. I liked those. There were some curves. What are these? Ah, here. So he's doing something like this. This is the first time when I've seen. Oh, if he also simulates them, yeah, then color me impressed. Let's see. So he fixes these faces and maybe pushes with the pressure or force here. Force. Oh, is something sticking out? Yeah, he inserted this at exactly near the face. So the profile of the reinforcement of the rebar is so big, the diameter, that it exceeds the geometry. So yeah, this is too big. It's not realistic at all. What did he do? He hit this body. So he didn't remove it from the FEA. He hid it. All right. Weird enough, I like this. Let's see if he's simulating. Also static. Why? Why static again? He's haunted by this rebar. Solve. Of course. What? It doesn't get out. It's the scale is wrong, but it doesn't get out. Let me tell you. No, it doesn't get out. The scale is wrong. If the scale were 1, then we would have had a nice behavior. He's unmaking. Come on. Aren't you frustrated because the wires get out? Come on, why? Learn ANSYS by Prashant. Come on, Prashant. You need to improve your game. 5 years ago. Now I think you are better than this, I think, yes. ANSYS tutorial. Reinforced. I don't want reinforced. Complete test. Slab in ANSYS so much. 5 years ago. We have one person watching. One person who didn't go to sleep. Modeling of reinforced concrete column, concrete beam, reinforcement concrete. Where is, yes, it's reinforced. Yes, very nice. Mr. Duncan just shows some, it's like, we can say it, yeah, it's like a tutorial, but he doesn't show animated results, let's say. All right, so what have we here? Concrete diaphragm wall subjected to biaxial bending moment using ANSYS. It looks reinforced, yes. It looks very nice. The scale is exaggerated. Look here. $240 the scale. Yeah, so not so cute. 240. Come on. He made again the capped, and the capped is also surfaces, and he made here 0. Why not 1? Why? It's static again. I know this person. We've seen it a few minutes before, maybe 15 minutes ago, because he uses these commands, APDL commands. Because I would like to attract beginners, I prefer not to insert such commands. Not that I would be an expert on APDL. I'm not an expert on APDL, but I know very well how to work in ANSYS workbench. This APDL interface, let's say, yeah, ANSYS product design language, I think it's the acronym. It's not user-friendly, so it has a very steep learning curve. It's not beginner-friendly. So this is why I will not show something like this, because you cannot attract beginners with something like this. This is my opinion. I have simulated a few years ago something like this. I wanted to show how these bollards, how they are crushed. Yeah, they aren't. They are not reinforced. Only, let's say, pure concrete. We don't have rotating wheels because the focus is on the concrete parts. This is something kind of similar, let's say, and you can see tetrahedral mesh, yes, and this is glass. It's also brittle fracture, but it's glass. They have two scenarios, a notch here in the middle and one displaced, and you can see how the fracture path is formed with classical traditional Lagrangian mesh. And in a few minutes we are going for the SPH, for the smooth particle hydrodynamics approach with the small spheres. Yes, what does our simulation do? It's finished. Let's see what changed. Oh no, I liked better the one with 0.2. This is too stiff, let's say. So let's go back towards 0.42 here for the geometric strain limit. And I promised you that we are changing the frame particle. We're going towards small spheres, towards smooth particle hydrodynamics. This is meshless. Yes, there will be no mesh, no traditional Lagrangian mesh on this part. So this being said, I can delete this. Instead, what I need to do is method, apply here. It gives a yellow warning because we need to select the latest, the particle. Let's choose again the 9 millimeter diameter and let's generate mesh. Ooh, it looks so nice, but what is the number of nodes? Oh, around the same. All right. So let's press it. Let's repeat. Does it work? Of course, clear generated data, yes, solve. I'll ignore for structural parts. Why not? Oh, and it stays here. Or it goes on. Ten minutes, yeah. Maybe it will be prolonged. 14, let's go, it does not go towards 30. Let's hope. All right. This is Nebacus. ANSYS space claim tutorial. RCC bridge peer modeling step by step. But don't tell me he is modeling from scratch. He is modeling from scratch. I thought he is importing from Revit or Archicad, but he's modeling from scratch. Oh yes, I like what he's doing here. 3-point loading. What is 3-point loading? Shouldn't it be bending? RCC beam. Why not RC beam? Static. Everyone is working with static. not everyone, some people. Pull out test of concrete in ANSYS workbench. Can we pull out concrete? Instead of the compression, let's see what he's doing. So here on the force, he will apply a force. What is this? With this, he will pull this face. All right, static again. Oh, let's not see the password. Engineering data, concrete. How will this, so many nodes, how will they find these nodes? Yeah, we should have had a sphere of influence refinement here. Do you have any question? No, there is no question. All right, so I'm interested. Now he's thinking about adding concrete, also from general materials, of course. And here, concrete, and another mine. Why minus? No. If it's a pull out, is plus. Look here at the. I don't know if you see it. Yeah. So he's going for minus, but he should be on plus because he's pulling out plus. No, this is not a pull out. Now he's changing. All right. 100,000. This is 10 tons. Finally, a more realistic load. No results? What? Of course, because of the amount of errors that appear. Oh my God, this I need to see. This is like a dam. It looks like a dam. So much work. Impact of tank shell on concrete wall, crash testing. Another capped isosurface, all right. Only this? Stirrups. Over a square column using ANSYS. ANSYS plain concrete beam nonlinear. This means I think there is no reinforcement. Exactly what I am doing today. Let's see how much it will take. 25 minutes. Let's see at least if we are on the correct path. We're on the correct path, and we can see already some fracture here. All right. Yeah. So there is this fracture in the middle. Should we leave it with let's make the sizing bigger. I don't want to wait 25 minutes. So particle method, instead of 9, let's make, I don't know, 11. 55. Almost half of what was. Yeah. Now I think we're going towards 15 minutes solving. Come on, give me 15 minutes in the end. 5, 7, and I think it will increase towards 10 or 15 minutes. All right. Let's see what we have here. Static, of course. He has made a name selection for these nodes. They will be the supports. He will fix this edge or what? Yeah, he fixed those nodes vertically. You could have very easily selected an edge, not necessarily nodes. And here, he's bending. What? Pressure. But come on. There is a symmetry, but you know what the problem is? It's like a 4-point bending. It's not 3-point bending because the symmetry should have been here on the middle of this brick or whatever, if it were to be 3-point bending, but it's a 4-point bending because the symmetry is here. Yeah, the symmetry about -6 axis. I'm curious if he selects the x-axis. Yeah, let's see. Symmetry, x-axis. Does he select the face? So he defined the symmetry offline. Come on, he doesn't show the symmetry, he doesn't show the face. He's showing the correct axis, but he doesn't show the face. This is important to show the face. This face. This one. All right, 8 megapascals. Why 8 megapascals? For pretty, it's kind of, it's pretty big, yeah? 50 centimeters, maybe 1 meter. And no, it's laughable. 8 megapascals, according to me, it's laughable. Contact, no separation. Yeah, so it was cooked offline. This is he's watching the. No, it's not. What? Hi, he copied from. Yeah. Why don't you use concrete commands? Oh my God! Please don't tell me you're using this. Oh no. Of course, this gets out. What? Bonded, yes, in order not to slide. What? Through scale? Why is 26 millimeters? It's like an hourglassing error, but it's, oh my god, 0. So yeah, if you make it 0, then it's perfect. ANSYS burn. Come on, what are you burning here, Mr. Mess? Come on, no, please don't publish something like this. Don't show to the people this. No, no, don't. Take your time to cook it. Then present it once it's made. 6 years ago. Come on. So this one I made 8 years ago, and it was one of my first simulations with plain and reinforced concrete. So what you have here, you have a detonation, and here this slab, let's say this plate is unreinforced, and this is reinforced. You can see the reinforcement. You can see also the explosion for a few seconds. For here, yeah. Let's see if we can catch it. Yeah, there was. So here, this is the exhaust plume from the detonation. And these are the gases, yeah, the detonation gases, let's say. And now these are displaced or inside the plume, the detonation plume, let's say. Yeah, it was pretty coarse, I admit it, but yeah, it was pretty unique at that time. Pretty unique also, I think, now, because I don't think someone has published detonation in reinforced concrete. Maybe recently, maybe someone published something in ANSYS workbench, maybe. Let's see our simulation. 40 minutes, so I predicted correctly. 40 minutes, let's see what it's doing. Yeah, it goes very nice. Very nice. So this speed is kind of too fast. This is why we have right here. It looks so nice. Let's adjust visible. All right. We have a high value because of these small spheres. They are getting out. A hint. When designing, normally the deformed part should be smaller than this punch, than this pusher. So let me tell you what I meant. These edges, this face and this face, Control F face, these two faces, should be more on the inside. I mean, this pusher should exceed the concrete plate, yes? Should be a little more enlarged or dilated laterally. Also here, yes? So in order to ensure that the concrete, the deformed part will be inside somehow. Yeah, they are exactly on the line, but the supports and the pusher should have been bigger. Look here, they are perfectly aligned. This is why sometimes we have something that slips off, it gets out. Yeah, also it gets in, it dives in. and we have these spheres getting out. Yeah. Every simulation can be optimized in time. So, ANSYS mechanics. Plain concrete. Do we have something? We have something similar to what he has done 2 minutes ago. Here, precision concrete, scarifying, and rebar. Oh my god, it's so nice. What is this? This video shows a powerful concrete scarifying process, removing damaged surface layers and exposing rebar with high precision. Here, it's removing this portion. Step by step, the machine improves surface quality, speeds up preparation, and boosts productivity for structure repair and construction efficiency. This is a mouthful. Yeah, nice. Heat transfer for concrete column. One system of such analysis of concrete column. Reinforced concrete. The same thing with capped isosurfaces. Again, capped isosurfaces, no real mesh erosion. Show us the ANSYS model. Compressive test. Concrete column, and he makes a cylinder and he compresses it. Wow. A fixation in the force or pressure. Come on. Why? Reinforced concrete tunnel. ANSYS civil fan. What? What is this? So I think these are some tunnels, yes? Oh, so nice. So the load increases because they are submerged underwater. I think. Or these can be soil, maybe. And they compress the tunnels. And we see the various deflection and moments that appear. This is kind of Spanish, I think. Tons per meter. So this is MD, of course, is the moment. This is the force, maybe something like bending force. And this is the displacement, what we call sag. Sag, this is the displacement. It would have been nice to have these colored in order to see which one is which, but we can see something like here. Yeah, this maybe this is the moment. Maybe it says okay. So moment. Yes, I was right. This is the bending moment. This is the carrying forces. Yes, the green ones, and versus axial forces. Yeah, so they are not the displacement, as I said, the sex. No, these are forces. So carrying forces and axial forces. All right, so, and these are the moment. Oh, yeah, very nice. I never seen ANSYS civil fem in action, so now I'm seeing it. did they do something else? Yes, ceiling film. Reinforced concrete tunnel. I think clavim over external. Okay. Finally, we have some deformations, and here are the moments. Yeah. Oh, we have cracks, if I see, yeah? Appearance of cracks, or crack formation, let's say. If these will unite here in this Y shape, then yeah, everything will collapse. Also, this is not funny here. Okay. Yeah, it's very serious. These dudes are professionals and they know what to do. Let's take a look at our scenario. 7 minutes, all right. Does it work as intended? Yes, I like it. Adjust to visible. We should ignore the higher values because they pertain to the small spheres that go above, and we care only here. Yeah, it looks so nice. Adjust to visible. Or maybe reset all. Yes, so it's no reinforcement at this moment. Let's make here, I don't know, 15. Does it help with something? Not at this moment. It's already cracked. You can see a proper stress distribution before the cracks appear, let's say. More visually pleasing here. Do we have any questions from the audience? No. Perfect. What have we here? Reinforced concrete tunnel of road something. Of road running underneath Madrid Barajas airport, several miles of the soil. Structure interaction was conducted as well as the dimensioning of the reinforcement needed in the tunnel for the different zones and the loads from tunnel backfield. Backfield with soil, yes. Frontal view of soil and tunnel mesh. Project cost. Some APDL here. This is. So civil FEM is. It's more akin, it's more related to ANSYS mechanical or APDL. Vertical movements on a critical zone of the tunnel junction. Principal stress of intersection of terminal building with tunnel. Yes. Axial force, bending moment. He has shown this in another clip. In event engineering. All right. So they have reinforcements, which will be for another time. ANSYS training. So let's learn. Nice model. He has reinforcement. So let's click reinforcement. What? He is in explicit dynamics. how many years ago? 6 years ago. He is in explicit dynamics. He should have used two body interactions, one reinforcement and one frictionless. This is my opinion, if I remember correctly. Yes. Yes. Fine. Yes, this is the correct setup. Too fine mesh here. Come on, please refine the mesh on the concrete, please. Yes, finally, something better. Maybe we'll have some fracture, maybe. It's not so important. Velocity, why? Why? It's easiest with the displacement. On the y-axis with plus, what value do you give? Let's see. 8 meters per second. Okay, let's see how you correlate it with the end time. Yeah, it's a good correlation. Fixed support, and so I didn't pay attention. The velocity is applied on the pusher. Okay. Yes. Do you have fracture? Let's see. Show me. Show me. Oh no, he's not modifying. I'm curious. So much time, you see? 45 minutes. Instead of 5 minutes or 15. So, show us. Have you seen the scale? Look here, 56, which is already so high. But what is not? Delete, of course. Of course you should delete. Yeah, when using velocity, it bounces back. Finally, through scale 1, it bounces back. You should not use velocity because you cannot control the pusher. You cannot gradually advance. Yeah, it's... And so many comments, no? And what? Damage, yeah, he has damage. I'm curious about the material. Let's look at the material. If he says something about... He doesn't say anything about the material. What? Come on. What? Please tell me you are showing the material. The concrete that I'm using, yes, from explicit dynamics. Too bad he does not know how to put proper boundary conditions. Yes, but maybe in the future, maybe he improved. After this point, maybe he improved. So fine mesh here and coarse here, and with no proper justification. Yeah. This is why the solving took 45 minutes or something. Yeah. I hope he improved. Mr. Mehdi Khatamifar. What is he showing here? Heat and mass transfer. Thermofluid mechanics. I think he's teaching for faculty. Mechanical engineering, something. Yeah. The fact that he's teaching, it does not necessarily mean that he is a specialist in FEA. For everything, it takes years. Yeah, for training purposes, yeah, for beginning, it's nice. James Cook University in Australia. All right. What's the structure? Maybe another time. I have heard the FEA stop. So come on, why don't you cooperate? What are you doing here? Why? So animation errors. We don't have plastic strain here with SPH. Here the scale is not correct. Let's make it true scaled. Maybe animate, maybe? No? Yeah, there is a bug here. There is a bug because you can see that the deformation is correct, but there is a bug. This seems that it will work. It looks like it will work. So, as I said before, the pusher and the supports need enlarged in order not to have this thing that appears here. In order for you to get a feeling of why these particles get out, I will also plot the velocity, and you'll see that it's too high. Seriously, I cannot animate? Yeah, it does not. I don't know what to do. Let's clear generated data and maybe scope only the concrete part. Let's see. Can we animate? No, come on, what kind of a bug is this? Why? Maybe reset all, maybe? Maybe reset all? Yeah, no. It goes towards infinity. You can't read here in infinite. So I will not investigate what is the cause of this glitch. I promised velocity value, and we're going on the x-axis. I don't know if I will. Does it work, the animation? I think not. No. But look here, yeah? Let's change towards meters. 34 meters per second multiplied with 3.6. We have 122 kilometers per hour. The pushing, yeah? The pushing of this part. So how we solve this, we're going here and we increase this value in order to have a proper time. Yes, of course the simulation will be prolonged, but it will be more realistic, and it will be a piece of cake for the ones working for a laboratory, for a company, because they have the necessary amount of licenses and hardware power. Let's go towards ending the stream. Nothing more regarding other messages. Thank you for the attention, and see you on the next live stream. Good night. That's all from my side. Bye-bye.